Welcome back. In this video we're going to discuss a theorem which states that the null space of a matrix is actually a subspace of its parent vector space. In particular, if we start with an M by N matrix, we say that the null space of A is a subspace of Rn. Note, n is the number of columns. Thus, vectors in the null space have to be of size n. This is because the definition of the null space is the set of all vectors such that when we multiply those vectors by A, we get 0. So we want to show that the null space is a subspace, and to do so we remember that there are three conditions that we have to meet. To show that the null space is a subspace of Rn, we prove each of the three necessary conditions. Number one, we need to show that 0 is an element of the null space. Okay. Well, to do this, we say, let's consider A times 0. In this case, this 0 would of course be of size n by 1, because in order to do this matrix multiplication, the inner dimensions must agree. But we know that a linear combination of the columns of A with scalar weights equal to 0 must be 0 in the output space. And in particular, we see that indeed, because this vector multiplied by A produces 0, by definition, the n by 1 0 vector must be in the null space. We've just satisfied our first condition to be a subspace. Condition number 2. We need to check that if x and y, an element of the null space of A, then the sum x plus y is also in the null space. Let's begin by assuming that we have two individual vectors in the null space. By definition, when we say that x and y are in the null space, that means that ax equals 0, because vectors in the null space multiplied by the matrix A produce 0, and it also means that ay is equal to 0. If we consider A times x plus y, we want to show that if we multiply A times x plus y, that we will indeed produce 0. In other words, the sum x plus y is in the null space. We know by superposition that we can distribute matrix multiplication over vector addition, which means A times x plus y is ax plus ay, but ax is 0 by definition because x is in the null space, and we also know that ay is 0 because y is in the null space. We know that 0 plus 0 is indeed 0, which implies immediately that the vector sum x plus y multiplied by A gets sent to 0, but this is the exact condition needed to confirm that a vector is in the null space. What we've just shown is that the null space is closed under addition. If you start with two vectors in the null space and you add them together, you will get a third vector in the null space. This was the second condition of the requirements to be a subspace, and we move on to the third one. Well, the third condition of the requirement to be a subspace says that if we start with any scalar and any vector in our subspace, in this case we'll just call it x, then the scalar vector product c times x must also be in our subspace. Well, we begin with the assumption that x is in the null space. which says immediately that if I multiply A times X, I will get the 0 vector. That was the definition of what the null space was. And now what we want to do is consider a scalar multiple times X. If we take A times this scalar multiple C times X, we want to show that this is equal to 0. If so, this vector multiplied by A would produce 0, and we could conclude that this is in the null space. However, we know by the homogeneity property of superposition, meaning that we can bring out this scalar, that C times AX is equal to A times CX. So scalar multiplication goes through. By definition of X, we know that A times X is 0, since X started in the null space, and we know that C multiplied by 0 is 0. This immediately implies that the scalar multiple times X is in the null space, but we've just concluded that if you have any scalar multiple times anything in your null space, that you will stay in your null space. In other words, the null space is closed under scalar multiplication. This was the third condition of subspaces of a vector space. With these three combined, we see immediately is a subspace of the vector space Rn. See you in the next video.